Have you ever wondered why aspirin is absorbed in the stomach while drugs like morphine are absorbed in the intestine? The reason is not the dose, not the formulation, and not even the route of administration, but pH and ionization. Every drug we give orally passes through the same gastrointestinal tract, yet each drug behaves very differently. And that difference depends on one simple question. In a given environment, is the drug charged or uncharged? Because only the uncharged form of a drug can cross biological membranes. To predict this accurately, we use a very powerful but often misunderstood tool in pharmacology, the Henderson Hasselbalch equation. And in this video, I'll make it so simple that you'll never forget it. So let's get started. When we administer a drug, for example, by the oral route, the very first and most crucial step for that drug to produce its intended therapeutic effect is absorption. In simple terms, absorption refers to the movement of the drug from its site of administration into the systemic circulation, that is, into the bloodstream. Until the drug successfully enters the blood, it cannot be distributed to various tissues. It cannot reach its target organ, and therefore it cannot exert any pharmacological action. For this reason, absorption is rightly considered the first and most fundamental step in the entire journey of a drug inside the body. Now, once we clearly understand that absorption is the essential initial step after oral drug administration, the next logical question that arises is, what factors influence how well a drug is absorbed? In reality, drug absorption is influenced by several factors, including the route of administration, the particle size of the drug, the solubility of the drug, specifically whether it is lipid-soluble or water-soluble. In addition to these, gastrointestinal motility, surface area and vascularity of the GI tract, presence of food, and most importantly, the pH of the surrounding environment and ionization state of drug all play significant roles. In today's discussion, we will focus specifically on the role of pH and ionization of drugs, which forms the basis for understanding the Henderson-Hasselbalch equation in pharmacology. Most drugs that we use clinically are either weak acids or weak bases, because strong acids and strong bases can cause significant damage to body tissues. When we take these drugs, or when these drugs dissolve in body fluids, such as the gastric fluid in the stomach, they do not remain in a single form. Instead, they exist in two forms, an ionized or charged form or uncharged form. This form is electrically neutral, meaning it carries no charge. Because of this, it is lipid-soluble and can easily dissolve in the fatty cell membranes of the gastrointestinal tract. As a result, this form can readily cross biological membranes, allowing the drug to be absorbed efficiently into the bloodstream. In contrast, the ionized or charged form of the drug carries an electrical charge, either positive or negative. It is water-soluble form but poorly lipid-soluble, which means it cannot easily penetrate the fatty cell membrane. As a result, once these drugs enters a fluid compartment, such as gastrointestinal lumen or the tubular fluid of kidney, it tends to remain confined within that space and can't diffuse back across the membrane. This phenomenon is known as ion trapping. For example, when a drug is filtered into the renal tubules, if the drug is ionized within the tubular fluid, it can't cross the lipid membrane of the renal tubules. And as the result, the drug is effectively trapped within the urine compartment and is excreted from the body. Thus, charged form is the form that is primarily absorbed, whereas the ionized form is effectively trapped and eliminated. So, the Henderson-Hasselbalch equation helps us answer a very practical and clinically important question. In a given physiological environment, will a drug predominantly exist in its charged form or in uncharged form? This prediction is extremely important because only the uncharged form of a drug can easily cross lipid cell membranes. Therefore, by using this equation, we can indirectly determine where a drug will be able to cross membranes, and, just as importantly, where it will fail to cross and become trapped. As most drugs that we use clinically are either weak acids or weak bases. From basic chemistry, we know that an acid is a substance that can donate a hydrogen ion, whereas a base is a substance that can accept a hydrogen ion. For simplicity, we represent a weak acid drug as HA, as weak acid can donate hydrogen ion, so it contains hydrogen ion, and a weak acid drug typically exists in equilibrium as HA can reversibly dissociate into H plus and A minus. And this dissociation is highly dependent on the pH of the surrounding environment. On the other hand, a weak base drug is represented as B, which can accept a hydrogen ion to form BH plus, again in a reversible manner. As a result, depending on the pH of the environment, a drug may shift between its ionized and unionized forms, and these forms can cross the membrane and these forms can't. Now suppose we take a weak acid drug such as aspirin, which is chemically salicylic acid. As a weak acid, this drug has the ability to donate a hydrogen ion. When this drug reaches the stomach, it encounters a highly acidic environment with a pH of around 1 to 2. In such an environment, there is already a high concentration of hydrogen ions present, and this excess of H ions pushes the reaction toward the left side. As a result, most of the drug remains in its unionized form, that is, as HA. This unionized form is lipid-soluble. Thus, the acidic environment of the stomach actually favors the absorption of weak acid drugs by maintaining them predominantly in their non-ionized form. Now we take a weak base drug such as morphine. As a weak base, this type of drug has the ability to accept a hydrogen ion. When this weak base drug reaches the stomach, it encounters a highly acidic environment. Because there is an excess of hydrogen ions present, these H ions readily combine with the weak base, shifting the equilibrium toward the ionized form, that is BH+. As a result, most of the weak base present in the stomach becomes positively charged. Since this ionized form is water-soluble, thus weak base drugs show poor absorption in the stomach. However, as the drug moves from the stomach into the intestine, in the intestinal environment, the pH becomes more alkaline, which means the concentration of hydrogen ions is lower. Therefore, fewer hydrogen ions are available to bind with the weak base, and the equilibrium now shifts back toward the unionized form. This unionized form is lipid-soluble, leading to better absorption. Thus, the key point to understand is that pH determines the direction of equilibrium. That is, acidic pH favor ionization of weak base, whereas alkaline pH favor the formation of uncharged, absorbable form of weak base. An easy way to remember this concept is when we place an acidic drug in acidic environment or basic drug in basic environment, essentially nothing significant happens. Just like when we mix water with water, nothing new formed. The drug remains in its unionized form. The reaction becomes significant only when a drug is placed in opposite environment. The Henderson Hasselbalch equation is nothing more than a mathematical representation of the concept that we have already understood till now. Up to this point, we have learned that a weak acidic drug remains uncharged in acidic environment and remain charged in basic environment. The opposite is true for weak basic drug. Henderson Hasselbalch equation allow us to quantitatively predict in a given environment or for any given pH whether a drug will exist mainly in its charged or uncharged form by using pH and pKa. The equation for weak acid drug is expressed as where we place the ionized form upon unionized form. An equation for weak basic drug is expressed as where we place the unionized form, that is B, upon the ionized form. An easy way to remember which form goes above and which goes below in the Henderson Hasselbalch equation is to focus on the protonated form. Always remember that the protonated form, that is the form that contains the hydrogen ion, is placed below in the equation. In the Henderson Hasselbalch equation, the pH belongs to the environment, such as the stomach, intestine, or any other body compartment, whereas the pKa belongs to the drug itself. Imagine that we place a drug into a solution and then slowly change the pH of that medium. At a particular pH, half of the drug will exist in the ionized or charged form, while the other half will exist in the unionized or uncharged form. That specific pH at which the drug is present equally in its ionized and non-ionized forms is called the pKa of the drug. In other words, pKa represents the pH at which the drug is exactly balanced between its charged and uncharged states. Now suppose we place a drug into a solution and slowly begin to change the pH of that medium. As we do this, we eventually reach a particular pH at which we observe that 50% of the drug exists in the ionized form and the remaining 50% exists in the unionized form. Let us assume that this specific pH of the medium turns out to be 3. By definition, this pH value is known as the pKa of the drug. In other words, when the pH of the environment is equal to the pKa of the drug is equally distributed between its ionized and non-ionized forms. Now we can ask from Henderson equation if this is true or not. If the pH of the medium is 3 and the pKa of the drug is also 3, we can put these values into the equation for a weak acid drug. Since pH minus pKa equals 0 in this situation, now we take the anti-log of 0, which comes out to be 1, which means that the ratio of ionized to unionized drug is 1 to 1. Thus, this mathematical result confirms what we already understand conceptually. When pH equals pKa, the ionized and unionized forms of the drug are present in equal amounts. Before we start applying the Henderson Hasselbalch equation to solve numerical problems, it is very important to revise a few basic concepts of logarithms. Let me ask a simple question. What is the logarithm of 100? Since 100 has 2 zeros, the log of 100 is 2, and correspondingly, the anti-log of 2 is 100. Similarly, if we look at 1000, which has 3 zeros, the log of 1000 is 3, and the anti-log of 3 is 1000. In the same way, 10,000 has 4 zeros, so its logarithm is 4, and the anti-log of 4 is 10,000. Now once this is clear, let's look at some negative numbers. For example, if we take 0.01, we can count the number after decimal, that is 1, 2, and therefore the logarithm of 0.01 is minus 2. Correspondingly, the anti-log of minus 2 is 0.01. Likewise, for 0.001, a logarithm of minus 3, and hence the anti-log of minus 3 is 0.001. So let's do a quick question now. Calculate the degree of ionization of a weak acid drug with a pKa of 3 in 2 different environments. First in the stomach, where the pH is 1, and then in the small intestine, where the pH is around 7. Conceptually, we already understand that when a weak acid drug is placed in an acidic environment, nothing dramatic happens. The drug largely remains in its uncharged or unionized form. Now, let us turn to the Henderson Hasselbalch equation to see whether it tells us the same or not. In the stomach, the pH is 1, while the pKa of the weak acid drug is 3. When we substitute these values into the equation, the difference between pH and pKa comes out to be -2. Now, taking the antilog of -2 is 0.01, which can also be written as 1 over 100. This means that the ratio of ionized to unionized drug is 1 to 100. Therefore, the Henderson-Hasselbalch equation clearly tells us that in the acidic environment of the stomach, most of the weak acid drug remains in its uncharged or unionized form. Since this unionized form is lipid-soluble, it can easily cross the gastric mucosal membrane. Now, when a weak acid drug is placed in a basic environment, such as the small intestine, most of the drug tends to exist in its charged form. To confirm this, we again use the Henderson-Hasselbalch equation for a weak acid. In the intestine, the pH is around 7, while the pKa of the drug remains 3. Therefore, the difference between pH and pKa is 4. Now, taking the antilog of 4, which is 10,000, which means the ratio of ionized to unionized drug is 10,000 to 1. In other words, in a basic environment, the vast majority of the weak acid drug exists in its ionized or charged form. Since this ionized form is water-soluble and poorly lipid-soluble, it cannot easily cross the intestinal mucosal membrane. As a result, weak acid drugs are poorly absorbed from the small intestine.